Hello again. We're back at statistics at Hudson Valley. We have in chapter 10 and 11, hypothesis testing. I hope you're now familiar with hypothesis testing and the 5-step procedure that we encourage you to use at Hudson Valley and in the textbook following along. But I also showed you that on previous videos. We're going to continue with that concept of the 5-step hypothesis testing, but we're going to look at a little bit different data. So far we've looked at mean data, the number of desks or the number of fuses. We also looked at proportion data, the percent of students, for example, that switched their majors at Hudson Valley. And we looked at a sample to see if the population changed on those three. Then in chapter 11, we looked at 2 populations to see if the populations were different. We can look at men versus women, their GPAs. We also looked at 2 populations in percent data, and the one in our textbook and in class was the 1%, the percent of young women and old women like perfume. We're going to continue on with that 5-step process in chapter 12, and we're going to use the F distribution. So I would like you to have your chapter 12 handout, your F distribution, and probably again your calculator to be handy. So I'm going to go over to the .cam to refer to your handout. Okay, so one thing nice about the F distribution, only in Hudson Valley, okay, not even in your homework, but in your test or in your final exam, on the F distribution, when step 2, the level of significance, we are only going to use 0.05. Okay, so the F distribution also is used in 2 completely different types of problem. The first problem is when we compare 2 variances. Maybe the variance of machine A versus the variance of machine B, the thickness. We know the means are equal, but we want to know if the variances are equal. That happens to be the null hypothesis. And that we use the F table. By the way, the F table is the 3rd table in your reference area on Blackboard. The other area we use the F distribution, completely different, is when we compare 3 or more means. Okay, 3 or more means. What's an example of 3 or more means? How about if I compare the GPA of my 9 o'clock class, my 10 o'clock class, and my 11 o'clock class of statistics? Are the GPAs equal? That's my null hypothesis. So let's go with the first example, comparing variances. And I have right here an example. Lammers offers limousine service from City Hall, Toledo, Ohio to the Metro Airport in Detroit. Sean, the president of the company, is considering 2 routes, one via US 25, a local route, and the other via 175, a highway. He wants to study the time it takes to drive to the airport using each route and then compare the results. He collects the following sample data, which is reported in minutes. Using the 0.10 significance level, is there a difference in variation? Okay, so I noticed that. I said it's always 0.5. So that is going to be alpha equals 0.05. There's a long explanation why 0.10 is 0.105, because typically it's a 2-tail, and when you divide it by 2, it's 0.05. But all you have to remember is alpha is 0.05. the first thing you will do is calculate the mean, standard deviation, sample size, and degrees of freedom for each set of data. So I'd like you to pause the video and calculate those. Okay, I'm going to write them down. Root 25. Well, the sample size is 7. Degrees of freedom is 7 minus 1 or 6. Excuse me. Standard deviation is 8.99. I-75. N is 8. Degrees of freedom is 8 minus 1 or 7. And the standard deviation of I-75 is 4.37. You'll notice I didn't put the average there. The average is actually not used when we're comparing. We assume the averages are equal. And in this example, they are very close to being equal. And we can say we've done a statistical test and they are statistically equal. Okay? So we've calculated sample size, degrees of freedom, and standard deviation. Before we even go to step 1, I want you to note that the larger standard deviation will always be the numerator. The smaller one will be the denominator. Okay? And that will become in very handy in a little bit. Step 1, almost always our null, and I'm going to write it right here, our null and alternate for variance data will be the variance of root 25 equals the variance of I-75, or it is not equal. Most of our examples are like that. I think in your homework there might be one different where it's more than or less than or something like that. Step 2, 0.05. I promised you that. Step 3, you will always use standard deviation or variance divided by variance. That is the formula. It's located on the 3rd page at the top of your 3-page formula sheet. Okay. So our numerator degrees of freedom is 6. Our denominator is 7. Why do I want that? When we look up our critical values, by the way, and when you read this, the F distribution is skewed. And it will always be a one-tail, and here's our critical value. Here's our do not reject our null hypothesis area, and this is our reject our null hypothesis. Critical value. Critical value, on my PowerPoint presentations, I blow it up, the F table, so it may be a little difficult for you to see. But I'm going to show it to you right here. We have degrees of freedom of, and I label numerator and denominator. This is your denominator, degrees of freedom, numerator. It was 6. Let's see, 6 and 7. 3.87, 6 and 7. 3.87 is our critical value on the F table. You'll notice it says F table here. Numerator and denominator. And what I want you to note is our numerator is the larger standard deviation. It is not necessarily the larger degrees of freedom. That's why I label it here, and you won't get confused when you look it up on the F table. Okay? when you calculate these, I hope you use the statistical functions, because that's the only way you're going to get the standard deviation. And this is good practice for the final. So let's come down here and calculate our F statistic. Here's our F. It's 8.99 squared divided by 4.37 squared. Excuse me. And we get approximately 4.23. Well, if we plot that, 4.23, it's very obvious it's in the reject. So our conclusion, reject the null hypothesis. So we are going to reject that, and we are going to say the variances are not equal. Okay? Not a bad hypothesis testing. One of the easier ones compared to what we've been doing the last couple of weeks with mean and proportion data. Okay? So that is it for comparing variance. Now we're going to go on and compare 3 or more means. I'd like you to pause, and I'd like you to read a little bit and go through my PowerPoint presentation. I would like to do the last example that I gave you. I think it's about page 425, number 7 in the book. Depending on the version, what edition of the book, we might be off a little bit. But we're looking at 3 different employees, and let's say the time that they talk on the phone to a customer. And we want to know, is the average time equal among the 3 employees? Is the average time each employee talks on the phone equal to each other? Or maybe is one employee talking too little, or talking more than they should, or unequal? Okay. Well, the good thing is, step 1, null and alternate hypothesis. This, when we're comparing 3 means, again, it is given to you on your formula sheet. The mean of employee A equals the mean of employee B equals the employee C. The alternate, you just copy the words directly from my formula sheet. At least one is different. 2 could be equal, but all this procedure shows you at least 1 is different. Alpha. Alpha, as I said, is always 0.05 for an F table. The test statistic. Okay, test statistic is F equals SST divided by K minus 1, which is degrees of freedom, over SSE divided by N minus K. Now, it's a complex fraction. You can do a little bit of algebra, so it's not, but some people, some books like to, because they name the top and they name the bottom. So I'm just going to leave it like that. And you're welcome to calculate the numerator and the denominator and then divide those two. Okay? So how do we calculate the degrees of freedom? The degrees of freedom, K is the number of columns. In this case, we have 1, 2, 3. So it's 3 minus 1, or 2. N, since the first N minus K is the second degree of freedom. Since the beginning of this class, N is the sample size. 1, 2, 3, 4, 12. The total sample size minus the number of columns is 9. So our 2 degrees of freedom are 2 and 9. Okay? So when we look up, let's look up our critical value in our F table. Now in our F table, instead of using numerator and denominator, this is an old one, this, C minus 1, or it's K minus 1. Well, in our example, K minus 1 was 2. And then this is N minus K, which is 9. So we're looking up 2, 9, 4.26. Again, K minus 1, N minus K, 2, 9, 4.26. So our critical value, 4.26, this is do not reject null hypothesis. And you can't see this. This is the reject if we get something greater than 4.26. That was all the easy part. Now the fifth step, the calculation. You're going to need 4 boxes. Okay? And in those 4 boxes, we're going to do a lot of calculations. But first of all, we look at our data. And in our data, we calculate. We do some totals here. We calculate our sample size, 4, 4, 4. We calculate a column mean, a column average. And in this case, it's 8.25. If I average those, it's 3. If I average those, it's 4. Now, I'm not even sure if I can show you all of these numbers. Okay, I'm going to push it up there. This is the individual data. Oh, I forgot 2 more things. I've got to calculate the sample size, which I use for here, and then the grand mean, which is the average of all the data points. And in this case, it was 5.08. What we're actually going to calculate is the variation within a column, the variation from column to column. How do we do that? Right here. The individual data minus the grand mean. So I'm going to calculate every data point, every data point minus the grand mean, every data point minus the grand mean, every data point minus the grand mean, every data point. So this first data point is from 8 this 8 minus 5.08, and I got 2.92. This next data point is going to be 6 minus 5.08, and it's 0.92. I would like you to pause and calculate all of these data points here. All of these data points. Now I would like you to calculate the individual minus its own column mean. Well, where does that come from? The individual data point minus its column mean. The individual data point minus its column mean. And I know I'm going up and down, but even in class, this is how we do it. This came from 8 minus 8.25. 8 minus 8.25. The next data point will be 6 minus 8.25. 6 minus 8.25. and I got a negative 2.25. Now in this B column, where does this number come from? It will be 3 minus 3. 3 minus 3, or 0. So now I'll give you an opportunity to calculate all of those. Calculate both this and that one. I'm sorry if I went off the view for there for a few seconds. Okay? I am going to show you a summary of the results. Right here. Okay? Here are those two tables I asked you to calculate. Every individual data minus the grand mean, and every individual data point minus its own column mean. Got these results. Well, if you observe, there's negatives and positives, so we can't look at the variation. So what we do with every one of these data points is we square it. See the square there? We take 2.92 squared, and we got 8.53. We square 0.92 and got 0.85. Square this, square that. We do the same thing for the lower table. So we squared negative 0.25 and got a positive 0.0625. We squared negative 2.25 and we got a 5.0621. Square 0, get a 0. Square negative 1, we get a positive 1. So these are just the squared values. I'll give you a chance to pause and look at all your data points. Okay, so now that you have all these squared numbers, notice here we're going to total them. You're going to total this column. Total this column and put it there. Total this column and put it there. When you add up these three numbers, you get SS total, the total variation from the grand mean. Really the sum of the squares total, because it's a squared number, from the mean. The lower one, same thing. We're going to total this, get a number, total this, get a number, total this. We add these three numbers, in this case got 12.75, and this is the sum of the squares error. It's the square error within a column. It's the error within a column. So where do we go from here? Okay. Well, so far we have SS total, which equals 74.95. We have SSE, which is 12.75. We also need an SST, which is different from the total. See, we need an SST. That is the difference between these. All you have to do is subtract it out, subtract those two, and we get 62.2. So this is the total variation, the sum of the squares variation from all the data points from the grand mean. This is within a column, and this is column to column variation. Now we have all the numbers we need in order to do our calculated S. Here's our formula. So SST is 62.2. This is the degrees of freedom, remember. 3 columns minus 1 is 2. Sum of the squares error is the error within a column, which we, from the previous page, the table was 12.75. And then the other degree of freedom, n minus k, or sample size 12 minus 3, and 9. When we do this calculation, we get 21.94. Well, if you remember here, here's our critical value. Heck, 21.94 is way the heck over there, right? Or even further. So we reject our, we reject our null hypothesis because 21.94 is greater than 4.26. So we reject that all three means are equal. And our conclusion is at least one is different. Well, let's look at it. Column means again. We rejected that these three are equal. It looks like one of them is not equal. Well, if you use a little bit of common sense here, that probably is the mean that's not equal. Okay? This is a long process. Okay? And what I've decided is this type of problem, you're going to have an Excel project. So be prepared. You're going to do it in Excel and do a lot of these calculations in Excel. I did not want to give you a test because one problem pretty much takes the entire hour. There is Excel. In your Excel, not only will I ask you to do it by hand, but I will also ask you to use the Excel function on the Fdistribution. So you can do it quick and easy, and you'll be able to check your results. So this pretty much concludes my presentation on Chapter 12, the Fdistribution. I do recommend you do the homework and a couple of more problems of the ANOVA tables. If you have any questions, let me go back. If you have any questions, don't hesitate to email me. Don't hesitate to look on Blackboard. You are welcome also to call me or come and see me during my office hour. Thank you very much and have a great day.